Hi, my name is Wichitwechkarn, and I worked on this project with Bende, Cristian Bodnar, Matthew Wales, and Professor Pietro Leo. In our work, we focus on neural relational inference. These models take in trajectories, explicitly infers the underlying interaction network, and uses this to predict the evolution of the system. In our case, we study simulated data using ideal springs, finite springs, and Coulomb interactions between 5 particles. Multi-relational networks can be viewed as multiplex networks where we factorize out different interactions. These can be generated by first generating networks for each layer and then combining them using different permutations. This is shown for 2 simple 3-node networks. Note that these form isomorphism classes where the A's are grouped together and the B's and C's are grouped together. The role of these isomorphism classes is the focus of our work. To generate all the possible multi-relational networks, we only need to consider combinations between a few networks for each interaction. We call these basis networks. Examples are given for 4 particles with spring and charge interactions. We present a method to find all the multiplex isomorphism classes given the basis networks we want to combine and their automorphisms. This method labels each combination with a string and groups them into isomorphism classes using automorphisms, which is much more efficient than having to check for isomorphisms for all the multiplex networks. We highlight the role of isomorphism classes on the performance of models. We show that evolutionary sampling of networks for each interaction to form multiplex networks, as in previous works, leads to a highly biased isomorphism class distribution, which adversely affects the performance of models. Previous works also do not control for isomorphism leakage between the training, validation, and test set. Some networks from different sets are therefore isomorphic to each other. Controlling for this possibility shows that the isomorphism leakage overestimates performance. We also show an example of using isomorphism classes to form benchmarks to investigate the generalizability of models. Finally, we compared the performance of prioritizing training examples individually by isomorphism classes and not at all. We show that prioritization by isomorphism classes produces the best results.